Okay, in this video, I will talk about basic notations about neural network with one hidden layer. Suppose we have the input layer. Which means how many features do we want to input. So suppose we use the old notation as in our regression. Suppose we have the xd input variable, and we denote the last d plus 1 equals to the constant, denotes a bias, and the hidden unit hidden layer. Suppose we have the second layer, we have the, so you can think it's just each unit, you can think this is a, first you do the linear transformations, linear combinations of current feature, and then active by some gate function, activation function. Okay, suppose we have the x1 hk hidden layers. Okay, also each hidden layer we also want to use a linear form, so we also want to have the hk plus 1 equals to 1. And suppose output, suppose we just say we only have one output. In future, actually in general, it's very common that a neural network has multiple output. Okay, maybe let's use a graph to represent deep learning with a network with one hidden layer. Suppose this is the D features. Suppose this is x1, x2, x3, x4. Okay, so in this case, D equals to 4. Okay, we have 4 input features. Okay, suppose now we have the first hidden layer. Suppose we call it A1, A2, A3, A4, A5. Okay, which is called a hidden layers. Okay, and suppose each hidden layer is a function. You can think of this as just a linear is transformation, like in the regression. If we want to get in the linear regression, if we want to get the nonlinear features, we need to construct new features, right? You can think of this as A1 is each of the hidden layer is a, so k equals to 5. Okay, and we have the x1, A2 is also a linear combination of all the features. Okay, similarly for the x4, x3. x4. Lastly, A5, last hidden layer, is also a linear function of all the input features. Okay, and each AI suppose just like, yeah, let's for simplicity, we only have one features, and then the output will be our function. We're gonna use this all complicated linear combination transformed by the nonlinear gate functions. We get this our approximate function f. So and we use this as our output y. Okay. So actually, the neural network model can be also rewritten as fx. Okay. Can be written as okay, maybe let's write down step by step here. So now suppose each hidden layer node unit a1 equals to a linear combinations of the current variable, including an intercept. We call it 1. Okay, a1 equals to w. So this is the first hidden layer node. So it's 1 0. So intercept plus yeah, maybe let's write down one by one. So the first hidden layer, the first transformed by the first variable x1. Okay, plus w1 2 x2 plus w okay 1 3 transform the third variable to the a1 plus w1 4 x4. Okay, so and then we transform by a nonlinear function, nonlinear gate function. Maybe let's write down here. Like the logistic transformation at the end. So for example, we can use a g. Let's use the g function and transform by this. We call this is our we call it a1. Okay. Similarly, a2. The second node equals to w2 0. Okay, the intercept plus w 2 0. Sorry. So the transformation from the first feature to the second node. Okay, w2 2 x2, w2 3 x3, w2 4 x4. Okay, and then you transform by some nonlinear transformation, and we do the same thing for each of the hidden layer node until the a5 equals to g w5 0 plus omega 5 1 x1 plus omega 5 2 x2 plus w5 3 x3 plus w5 4 x4. Okay, so and after we transform from the hidden layer, we also want to have the intercept here. Okay, and then we transform to the f, and then this fx equals to this beta 0, the last layer. So to the output, beta 0 plus beta 1 a1 plus beta 2 a2. Okay, so this is our fx plus beta 3 a3 plus beta 4 a4 plus beta 5 a5. Okay, so you can think this each line represents there some weight to beta 3, beta 4, beta 1 2 3 4 5, beta 0. Okay, and also Yes, and then maybe we can also label the weight. So if you transformation to the note one, so we use it to denote omega 10. Okay, transformation from the intercept to 1, and the a and the w 1, right? This is w2 1, w1 2. This is w1 3, w1 4. Okay, so each line represents a node, represents a weight for this linear combination. So actually we can use a simple line mathematical notation here is just the beta 0 plus summation the number of the hidden layers k from 0 including the k from 1 to capital K, number of the hidden layers, okay, beta k multiplies the ak, right? And this equals to beta 0 plus summation k from 1 to k, and the beta k and the g, okay, wk0 plus j from 1 to d features. We have d features, right? From 1 to d omega is transformed to kth node. So kth node transformed from j's feature and multiply the xj. xj. Okay, so this math notation represents the neural network with one linear function. Neural network with one hidden layer. And actually, the common choice for this gate function, okay, this gx, commonly choose as sigmoid, like a logistic function. Okay, another choice is called ReLU. This function actually is easy. This is represented by the positive part of a number. Positive part of a number, which can be represented as a stepwise function. If z is less than 0, we get 0. If z is positive, we just use z. Okay, actually, the same logistic function can be used to convert the linear function to probabilities, but actually, it's more modern neural networks. ReLU activation is more popular to use. ReLU activation can be computed and stored more efficiently than the sigmoid activation function. Although its thresholds at 0, because we apply it to a linear function, the constant term wk0 will shift this inflection point. So in other words, the model derived the 5 for example, in this example, if we apply the ReLU activation function, we derive these new 5 features by computing the 5 different linear combinations of the x, and then squash each through an activation function g and transform it. the final model is also a linear function of this new derived variable. So you can think of this as a new features, okay, like in the linear regression setting. New features. Each hidden layer is new features, like transformed based on the original features. There is another type of name, another name called this function, call it activation function. These are very important. Without this activation function, without this activation function, this is just linear combinations of the current, and at the end, even you have the multiple layers, your final model will be a linear function of the linear functions, linear combination of linear functions. So it's still linear. So activation makes the our function f(x) to be able to capture the nonlinear, and plus the interactions among variables. Okay, so here is one example. Here is one more example from our textbook. Suppose our d is equals to 2. We have two features. So we have two features x1, x2 as input, and k equals to 2. We have two hidden layers, like hidden layer 1, hidden layer 2. And suppose our activation function is gx equals to x squared. Okay, just the quadratic activation function. So let's see, and then suppose after we running the linear deep learning algorithm, we get beta 0 equals to 0, beta 1 equals to 1/4, beta 2 equals to negative 1/4. Okay, and W10 equal to 0. Suppose we don't, after estimation, those coefficients are 0. Okay, two hidden layers, the intercept terms are 0. 1 from the first variable is 1. From the first variable is 1. W1, 2 from second variable to the first node will be 1. W2, 2 is equal to negative 1. So actually, so if you think about applying to this this formula to our hidden layers, we can get the first hidden layer node will equals to the j function, right? So here the j function is x squared. So we have the, no matter what we have here, inside is this linear combination. So it's 0 plus x1 plus x2 square. And the second hidden layer unit is equals to 0 plus 1 minus x2 square. Okay, and our final function f(x) is just equals to beta 0 is 0 plus 1/4 hx1. So it's x1 plus x2 square, and minus 1/4 x1 minus x2 square, which equals to 1/4 x1 square plus x2 square plus 2x1 x2 minus x1 square minus x2 square plus 2, because minus plus, so x1 x2. So, and we cancel these terms, we get and 4 cancel the coefficients here, right? So we get x1 x2. Okay, So this is one example by applying this two neural network with one hidden layers, we can get the interaction terms between x1 and x2. So this is another simple example of the neural network. Actually, this example I just showed you is a neural network with one hidden layer and with a single output. But in deep learning setup, the most successful modeling result given by the neural deep learning is by the multiple output. So network with one hidden layer. For multiple output. Okay. The setup is similar to before, so we have the input layer. So it's x1, x2, xd. Okay. We have the one hidden layer. So it's h1. Don't forget the intercept term. h1, hk, say there hk. And the hk plus 1 equals to 1. And one output layer. So it's z1 and z. Maybe let's use the index big L. Maybe let's follow the textbook's notation. Let's use the z. Suppose we have the capital M outliers. Okay, and actually we have the okay, maybe let's use just one simple example. You can see what I'm talking about here. Suppose d equals to 2. Suppose we only have two features in our data. So it's x1. Okay, and this is x2, two features. And we have the one features. Maybe I can use different color. It's not really feature, but just the constant term. Okay, suppose now we only have one layer, but we have each layer we have the 3. So k equals to capital K is equal to 3. So we have 3 hidden layers. H1, H2, H3. Okay, so and the weight, do you still remember the notation for weight? Suppose we call this weight matrix is V. Okay, so this is the V matrix, and we denote the W to be the last hidden layer, from hidden layer to the output. So and the output we have the M output. So suppose the capital M equals to 2. Suppose we have two output, which is Z1 and Z2. So two input feature, two output value. Okay, so this weight will denote from the first hidden node, right? From the first feature V11. Okay, this is V12. Okay, and this one we call it V. Okay, if we want to use a matrix notation, then let's denote this V will be 3 So it's K, V is a matrix with K by D plus 1, okay, which is 3 times 3 matrix. So, and the last row is a constant 1. So here we just use the 1, 3 to denote this weight. And the second one, okay, we have the V 21, V 22, V 23. Okay, and the last variable we have this weight, this weight. So we have the V31, V32, V33. Okay, so therefore this V is a vector. You can think the first row is just the first row is all weight transformed to the first hidden node. So this is V11, V12, V13. Okay, the second variable is V21, V22, V23. Okay, last one is V31, V32, V33. Okay, and also we have the output node with also with constant 1. Maybe let's use different color for this constant. Okay, we have the W to the first output, so it's 1 1. W 1 2. W 1 3. W 1 4. Okay, so this one is W 2 1. W 2 2, right? W 3 2 3. W 2 4. And okay, so we have all the weights here. So weight, the W is a matrix of the dimension with dimension k times sorry, it's not a k, it's m by k plus 1. Okay, you transform from the k plus 1 hidden nodes to the m output. Here is you transform from the d plus 1 input to k hidden features. So the W equals to, so W will be a matrix, okay, with 2 output times k plus 1, so it's 4. So it's W 1 1, W 1 2, W 1 3, W 1 4. So these are always transformed from all the hidden nodes to the first output. We also have the W, all the hidden nodes to the second output, 2 2, W 2 3, W 2 4. Okay, so that's some basic notations. And then suppose we can apply some activation functions at each level. So suppose we denote, we introduce some new notation. So for each vector v, okay, we can apply the activation function to this vector. If we which means we apply it to each component wisely. So which means we apply to each component. If we have the subindex 1 here with a vector v, so we denote what we mean is we apply to the each element, we apply the activation function s to each of the element in the vector. Okay, and we also apply the last one. We just leave last one is equal to constant one. Okay, in other words, if we denote our H to be the hidden layers, okay, hidden layer vectors, so which means H equals to H1, H2, H3, H1, H2, H3, and 1. Okay, this is just equals to S1 multiply. We apply this to the vector v times x. Actually, if you notice that v matrix times x equals to let's rewrite this here. Is v times x. Okay, this equals to this one times multiply the x, right? So it's x1, x2, and constant 1. Okay, so this actually this this multiplication will be 3 by 3, right? And 3 by 1. So this is 3 by 1 vector, and the first element is just the weight. Here is just the v 1 k or v1d, sorry. Let's use I notation. v1 I from 1 to 2. Maybe let's do not use some math notation to confuse you. Maybe you can just say it's v11 x1 plus v12 x2 plus v13 constant intercept term. Okay, and we have the v transform to the second hidden layer from the first feature. Transformation from the second feature to the second hidden node, x2 plus v from the third features to the hidden node 2. Okay, and we have the v first variable to the third hidden layer plus v32 x2 plus second node, yes, v33. Okay, and then we apply this sigmoid function to each of the variable, which gives us equals to, but we augment with 1. So the last one is we add 1 here. So we have the sigmoid or the sigmoid function or ReLU function. We apply the to each by using each feature I. So it's V. This is to the first node, right? So from using i's features to the first node, and I from 1 to 3, right? And this is S I from 1 to 3 V 2I XI. Okay. No. Actually, it's only from to 2. We're gonna have 2 features. To 2. And plus the constant term V1 3. Okay, plus V2 3. S I from 1 to 2 V 3I XI plus V3 3. Okay, so this is what it means here. We use the matrix notation to simplify and then we apply so this is the first layer, and the second output we continue to get z output vector equals to, we apply the activation function to this w times h. Okay. Yes, w times h. Recall w is a vector. Remember, w is a vector with dimension. How many output we have, right? We want 2 output with the how many hidden layers, how many hidden units in that layer plus a constant. So this is a 3 hidden layers plus 1. So w is 2 by 4 vector times h. H is 4 by 1, right? So this will be a 2 by 1 vector, and you apply this vector component wise to this activation function. Okay. So actually we just write down this. We can use the matrix notation to write down, even we have multiple layers, we can simply using this matrix notation to denote our function. And the neural networks often have more than one output. This allows us to build multiple classifiers that share the hidden units. One of the advantages of using the neural network is that if you train multiple classifiers simultaneously, sometimes some of them came out better because they can take advantage of particular useful hidden units that first emerge to support one of the other classifiers. We can add more hidden layers. For example, for the image recognition, like a MNIST dataset, it's common to have the up to using two layers or up to 100 or 200 hidden layers. I think the common is if you have the first time you want to try your deep learning models, you want to try this dense model with 100 layers. It's very common. There are many variations you can experiment. Yes, and we will give you more details, and you can see more examples in lab and homework. And in next video, this is our model now, right? So next, the point is how do we estimate the parameters, like how do we estimate this V matrix and W matrix? Okay, and then it's about training our model. Maybe this video is a little bit long. I'll give more details in next video.